Solve this equation, where x and y are integers. This is a Diophantine equation. There are two variables in one equation, so there might be more than one solutions. How to solve this equation? Usually there are different ways to solve this kind of equations. For example, one way might be to convert the equation to the product of two algebraic expressions of variables of interest equals a number. Due to the variables of interest are integers, so each algebraic expression is an integer factor of the number. This leads to a system of equations. Then solve the system of equations, and find the integer solutions of the original equation. It seems not easy to do that for the given equation. Another way might be to divide the problem into different cases, and narrow down the possible ranges of variables of interest. Then find the integer solutions for each case. Because the left side of the equation, x squared minus y squared all squared, is greater than or equal to 0. So the right side of the equation, 1 plus 16y, must be greater than or equal to 0. As y is an integer, so y must be greater than or equal to 0. In addition, because 1 plus 16y cannot be equal to 0, so x squared minus y squared all squared cannot be equal to 0. That is, x squared cannot equal y squared. This implies that x cannot equal plus or minus y. So there are two cases: either the modulus of x is greater than or equal to y plus 1, or the modulus of x is less than or equal to y minus 1. Take y equals 2 for example, then x cannot equal 2, and x cannot equal negative 2. Y plus 1 is 3. So x is greater than or equal to 3, or x is less than or equal to negative 3. Y minus 1 is 1. So x is greater than or equal to negative 1, and is less than or equal to 1. For the modulus of x is less than or equal to y minus 1. As this inequality only makes sense when y is greater than or equal to 1. So y minus 1 is greater than or equal to 0. The inequality still holds when squaring both sides of the inequality. So we have x squared is less than or equal to y minus 1 all squared. Multiply the inequality by negative 1, then add y squared. We have y squared minus x squared is greater than or equal to y squared minus y minus 1 all squared. Y squared minus y minus 1 all squared equals 2y minus 1. As y is greater than or equal to 1, so 2y minus 1 is greater than 0. And y squared minus x squared is greater than 0. So the inequality still holds when squaring both sides of the inequality. So we have y squared minus x squared all squared is greater than or equal to 2y minus 1 all squared. Similarly, for the modulus of x is greater than or equal to y plus 1. Squaring both sides of the inequality, we have x squared is greater than or equal to y plus 1 all squared. Then subtract y squared from both sides of the inequality, we have x squared minus y squared is greater than or equal to y plus 1 all squared minus y squared. Y plus 1 all squared minus y squared equals 2y plus 1. As both x squared minus y squared and 2y plus 1 are greater than 0. So square both sides of the inequality, we have x squared minus y squared all squared is greater than or equal to 2y plus 1 all squared. Note that the left side of inequality 1 is y squared minus x squared all squared, which is actually equal to x squared minus y squared all squared. The right side of inequality 1 is 2y minus 1 all squared. The right side of inequality 2 is 2y plus 1 all squared. Clearly, 2y plus 1 all squared is always greater than or equal to 2y minus 1 all squared when y is greater than or equal to 0. Therefore, from inequalities 1 and 2, we know that x squared minus y squared all squared is greater than or equal to 2y minus 1 all squared. And it holds for all cases. We are given that x squared minus y squared all squared equals 1 plus 16y. So we have 2y minus 1 all squared is less than or equal to 1 plus 16y. 2y minus 1 all squared equals 4y squared minus 4y plus 1. Rearrange and simplify the inequality. We have 4y squared minus 20y is less than or equal to 0. Divide the inequality by 4. We have y squared minus 5y is less than or equal to 0. Y squared minus 5y can be written as y times y minus 5. And we know that y is greater than or equal to 0, so y must be less than or equal to 5. So to find solutions, we only need to check each possible value of y. Y can take value 0, 1, 2, 3, 4, or 5. When y equals 0, 1 plus 16y equals 1. Then x squared minus y squared all squared equals 1. So x squared minus y squared equals plus or minus 1. That is, x squared equals plus or minus 1. But x squared cannot equal negative 1. So x squared equals 1. Then x equals plus or minus 1. So xy equal plus or minus 1, 0. When y equals 1, 1 plus 16y equals 17. Which is not a square number. So there are no integer solutions, when y equals 1. When y equals 2, 1 plus 16y equals 33. Which is not a square number. So there are no integer solutions, when y equals 2. When y equals 3, 1 plus 16y equals 49. Then x squared minus y squared all squared equals 49. So x squared minus y squared equals plus or minus 7. That is, x squared equals 16 or 2. But 2 is not a square number. So x squared equals 16. Then x equals plus or minus 4. So xy equal plus or minus 4, 3. When y equals 4, 1 plus 16y equals 65. Which is not a square number. So there are no integer solutions, when y equals 4. When y equals 5, 1 plus 16y equals 81. Then x squared minus y squared all squared equals 81. So x squared minus y squared equals plus or minus 9. That is, x squared equals 34 or 16. But 34 is not a square number. So x squared equals 16. Then x equals plus or minus 4. So xy equal plus or minus 4, 5. It is easy to verify that they all are solutions of the given equation.